Welcome to this discussion of non-stationary capability analysis. This is a new procedure that's been added to Statgraphics version 20. Non-stationary capability analysis, like other capability analysis procedures, is used to compare process performance to specification limits. It is useful when the mean and/or the standard deviation are not constant over time. The procedure provides moving estimates of process parameters, of capability indices, of defects per million, and of the sigma quality level. The procedure provides a better estimate of capability than fitting a single distribution to all of the data. As an example, consider these 200 measurements of the breaking strength of glass bottles. You'll note in this data changes in both the mean and the standard deviation. The mean appears to start out fairly high, then drops toward the center of the sampling period, and then starts to rise again. The standard deviation, on the other hand, seems to be considerably smaller in the second half of the data than in the first half. In this video, we're going to concentrate on three capability or performance indices. The first index is PP. It is the distance between the upper spec limit and the lower spec limit divided by 6 times the estimated standard deviation of the process. That's a two-sided performance index. The second index is PPK. This is the minimum distance between the estimated mean and the specification limits divided by 3 times the estimated sigma. Finally, we'll look at DPM, defects per million. This is the items per million beyond the specification limits. I've loaded the data into the Statgraphics version 20 data sheet. You'll notice 2 columns, one indicating the time at which the samples were taken, and the second indicating the measured breaking strength. To do a standard capability analysis, that is, one where we assume the mean and standard deviation remain constant throughout the sampling period, you go to SPC, Capability Analysis, Variables, Individuals. I'll tell it that the data are in the column called Strength. The time indices are in the column called Time. Now the specification for strength is 250 plus or minus 30. That means that the lower specification limit is 220, the nominal value is 250, and the upper specification limit is 280. In terms of output, I'm going to tell it to take all the defaults. That includes, for example, assuming it comes from a normal distribution. When I press OK, it'll show me a list of tables and graphs that I can create. I'll stick with the defaults: an analysis summary, a table of capability indices, and a capability plot. When I press OK, it will open up a standard analysis window. Let me go ahead and double-click on the process capability plot so we can get a better look at it. Here you see a histogram of the data with the best fitting normal distribution. The taller vertical lines are at the lower specification limit, the nominal value, and the upper specification limit. The shorter vertical lines show the mean plus and minus 3 sigma. Thankfully, the shorter lines are inside the specification limits where we'd like them to be. The estimated performance indices are on the right-hand side of the graph. PP is 1.06. That's because the specification limits are a little bit bigger than the 6 sigma spread of the data. PPK is coming in at 1.03. That's comparing, in this case, the upper specification limit to the mean plus 3 sigma. Finally, the long-term defects per million is estimated to be 1,581. Standard rules of thumb say that PPK and PP should be at least 1.33. Unfortunately, we haven't achieved that in this particular analysis. We're now going to move to the new non-stationary capability analysis. To run this procedure, you go to Statlets on the main menu, find Process Capability Analysis, and select Non-Stationary Capability Analysis. The data input dialog box is the same as the previous procedure. I'll put in strength, time, and then the specs are 220, 250, and 280. When I press OK, I'll get a small analysis options dialog box. Here there are two things I can choose. I can choose to base the analysis on a normal distribution or a log normal distribution. The default is normal. I can also choose the type of smoother that I want to use to estimate the mean and the standard deviation. I can use one that assumes that at the end of the sample period, the statistics are constant, or instead are following a linear trend. Normally, you'll just want to take the defaults and press OK, at which point it will open up a Statlet window. If you've not used Statlets before, what they are is interactive windows. They have a control bar across the top with various options that I can change. For example, there's an option specifying what I wish to display. In this case, I'm displaying the data. There's a scroll bar specifying the width of the smoothing window, and I'll explain that in just a moment. And then there are some check bars where on certain graphs I can add sigma quality level targets. Now what you're seeing here is an estimate, a moving estimate of the mean, that's the red line here, and also the mean plus and minus 3 standard deviations. Both the mean and the standard deviation are being estimated using something we call Loess smoothing. Loess smoothing takes a window covering a certain percentage of the data, moves the window from the start of the sampling period to the end of the sampling period, and within each window estimates, using a moving average, the mean and the standard deviation. Right now, it's using a window covering 20% of the data at any particular point in time. That gives a fairly detailed estimate of what's happened to the mean and the standard deviation. Perhaps not as smooth as I'd like. If I use the scroll bar, I can increase that smoothing window. And what you'll see is you'll see changes in the mean and the mean plus 3 sigma. And in this case, for this data, I think if I move up to a window of about 50%, I get a pretty good estimate of what was happening in this particular process. The mean started out a little high with relatively wide variation. The mean then dropped as we went through the sampling period before it started to rise again. And you can also see a significant tightening of the 3 sigma limits. If I go up on the toolbar to the list box labeled display, I can choose instead the mean and sigma. This will show me how my estimates of the mean and the standard deviation have changed throughout the sampling period. As expected, the estimated mean starts high, drops throughout the first half of the data, and then rises again as we get toward the end. The standard deviation, on the other hand, starts out high, drops fairly consistently throughout the first 80% of the data, then levels off for the last 20%. Some other statistics I'd like to see are the capability indices. I'll go up to display and ask for those. Here you'll see the estimated values for PP, that's the two-sided performance index, and PPK, that's the one-sided performance index. I had mentioned before that we like both of those indices to be at least 1.33. That corresponds, incidentally, to a 5.5 sigma process, according to the 6 sigma methodology. If I go up and check 5.5, you'll see a reference line added where the indices are at 1.33. You'll notice they start out significantly below that target, but in the last third of the process, both indices are well above 1.33. I can also go ahead and display the defects per million. Defects per million, that's the number of parts per million beyond the specification limits, started out quite high, above 4,500. It then dropped throughout the sampling period to a very small value near the end. Now, if you'd like to see those small values a little bit better, I can press the right mouse button, go to Graphics Options, and choose the Y-axis. I'm going to tell it that I'd like it to display the scaling as powers of 10. I'm also going to tell it to please hold that scaling constant and start the scaling at 0.01. Then when I press OK, you can see a little bit more detail toward the bottom right. In fact, the defects per million has dropped below 1 for a good part of the sampling period. It's definitely below the target level for a 5.5 sigma process, and if I click on 6, you'll see it's also below the DPM target of 3.4 defects per million that corresponds to what people call a 6 sigma process. For those of you who practice 6 sigma, we can also display the sigma quality level. If I go up to the list and ask for SQL, you'll see a plot of the sigma quality level for the process at various time periods. We started out at the beginning as being about a 4 sigma process. But by the end, we've actually moved up to a 6.5 or 7 sigma process. That's definitely world-class quality. There's one more graph available in this non-stationary capability analysis statlet, and that's a probability plot of the residuals. The residuals are the deviations between the observed data values at any particular point in time and the estimated mean. We made the assumption that these residuals, these deviations from the mean, followed at any particular point in time a normal distribution. If that's true, if we plot the residuals on a probability plot, they should follow a straight line. This data is actually quite good. One final comment. It's interesting to compare the results you get if you assume one single stationary normal distribution to the non-stationary approach which I've described here. Here you see a comparison of the capability indices. In the case of the non-stationary approach, I'm showing the average values throughout the sampling period. You'll notice that the averages obtained through the non-stationary analysis are quite a bit better than those numbers you get assuming a single normal distribution.